This presentation is for the World Congress on Industrial Control Systems Security 2017. Hello everyone, my name is Văn Long Do from Viettel Research and Development Institute, Hanoi, Vietnam. Today, I would like to present my work entitled A Simple Algorithm for Jointly Detecting and Classifying Cyber-Physical Attacks on Industrial Control Systems. My presentation is divided into 5 parts. Firstly, we highlight the security of industrial control system against cyber-physical attacks. Secondly, we talk about the system and attack models. Thirdly, we describe in detail the proposed attack detection and isolation algorithm. Then, we give some simulation results for demonstrating the effectiveness of the proposed method. Some concluding remarks and perspectives will be drawn in the final section. Let us begin with the security of industrial control system against malicious attacks. Supervisory control and data acquisition system, or SCADA system, are highly distributed control systems used to control and monitor geographically dispersed assets, often scattered over thousands of square kilometers. The SCADA system has been found in most of safety-critical infrastructures, including electric power grids, water networks, or gas pipelines. The architecture of a typical SCADA system consists of 3 layers: physical layer, automatic control layer, and supervisory control layer. The operation of modern SCADA system depends heavily on the communication network for exchanging data between the control center and field devices and vice versa. Along with the development in communication technology, modern industrial control systems are becoming more and more vulnerable to cyber-physical attacks, not only on the physical infrastructures, but also on the communication network and the control center. These vulnerable points have been exploited to perform malicious attacks on real SCADA systems. For example, in 2010, a computer worm startup was designed to attack Iran's nuclear centrifuges. From an infected computer, the virus was able to penetrate into PLC of Siemens without being detected by traditional information security methods. Therefore, it is necessary to design attack detection and isolation algorithm in order to avoid catastrophic damage, economic losses, or even human life. The attack detection and isolation methods found in the literature can be broadly classified into 3 main categories: information technology approach, non-parametric approach, and parametric approach. The information security approach focuses mainly on the authentication, access control, and message integrity for ensuring the secure transmission of data packets among entities in the network. The non-parametric approach consists of analyzing hidden patterns in observed data. The detection and classification problems can be solved by utilizing monoclass classification and multi-class classification techniques, respectively. On the other hand, the parametric approach is based on the system and attack models. The decision-making process is based on the comparison between the system observation and the model output under the presence of nuisance parameters and random noises. The problem is generally solved by the analytical redundancy approach, which consists of 2 steps: residual generation and residual evaluation. The so-called residuals are first generated by Kalman filter or parity space techniques for eliminating the negative impact of nuisance parameters. They are then evaluated by revising classical chain point detection and isolation methods for circumventing the negative effect of random noises. Let us continue with the system and attack models, as well as the criterion of optimality for the attack detection and isolation problem. First, let us describe in detail the model-based approach for solving the attack detection and isolation problem. This approach consists of developing the system and attack models. The model of industrial control system is obtained from a set of equations describing the operation of the system under normal operation. The model of malicious attacks can be obtained by investigating the vulnerability of industrial control systems. For example, Smart attackers can perform coordinated attacks by designing the attack vector APK on physical processes, the attack vector AQK on the control signals, and the attack vector AYK on the sensor measurements. Our problem is to design the attack detection and isolation algorithm for jointly detecting the attack instant and classifying the attack type based on the sensor measurements and the system models. Under normal operation, the SCADA systems are described by the discrete time state space model driven by unknown system states and Gaussian noises. The cyber-physical attacks are modeled as additive signal of short duration L injected into both system equations at an unknown attack instant K0. For the attack detection and isolation problem, the attack vector AK is modeled as attack profiles theta1L, theta2L, theta-LL, where the index small l denotes the attack type and the attack big L stands for the attack duration. It should be noted that each attack scenario will lead to a particular attack profile, which can be calculated from system dynamics. The problem consists of jointly detecting the attack instant K0 and identifying the attack type L for a given criterion of optimality. In the attack detection and isolation problem, there are four possible scenarios: false alarm, false isolation, correct detection and isolation, and misdetection. The criterion of optimality involves the minimization of the worst-case probability of misdetection, subject to acceptable levels on the rate of false alarm and false isolation. The false alarm rate is measured by the worst-case probability of false alarm within any time window of predefined length. The false isolation rate is defined as the worst-case probability of false isolation within the attack period. The detection and isolation problem consists of finding a pair T and nu, where T is the stopping time at which the final decision nu is decided. Let us describe now the proposed attack detection and isolation algorithm. The proposed algorithm consists of two steps: residual generation by using the command filter technique and residual evaluation by revising classical chain point detection and isolation method. In this work, we use the steady-state command filter for generating a sequence of innovations. The state estimate X hat and the output estimate Y hat are described by the equation 3.1, when the steady-state command gain K can be obtained by solving the algebraic Riccati equation. The innovations are calculated by subtracting the sensor measurements by the output estimate. The statistical model of innovations is described by the equation 3.2, where psi k are independent identically distributed Gaussian vectors, and phi1, phi2, phi-L are transient profiles which can be calculated from the attack profiles theta1, theta2, theta-L as in equation 3.3. By stacking the last L observations, we obtain the statistical model of residuals as shown in the equation 3.4, where the vector of random noises psi follows the multi-dimensional Gaussian distribution with diagonal covariant matrix sigma. The vector of transient profiles phi is modeled as in equation 3.5. The statistical model in equation 3.4 will be used in the following for design the attack detection and isolation algorithm. The classical chain point detection and isolation algorithms found in the literature such as window-limited QSUM, matrix QSUM, or vector QSUM are suitable to the problem of detecting and isolating abrupt changes, that is, the changes of infinitely long duration. In this work, we propose the simple finite moving average or FMA algorithm for solving the attack detection and isolation problem. This algorithm is described in the equation 3.6. The stopping time T FMA is rate if there exists at least one index L different from 0 such that all the log likelihood ratios between hypothesis HL and other hypotheses are greater than or equal to a chosen threshold H. The final decision nu FMA is such an index L. The log likelihood ratios are calculated in the equation 3.7. Let us continue with the application and numerical examples. In order to validate the theoretical results, we have developed the simulation model of a simple SCADA water distribution network. This water network consists of 2 treatment plants, 2 pumps, 2 reservoirs, a tank, several pipelines, and 2 consumers. It is assumed that the attacker is capable of stealing water from the reservoirs, turning off the pumps, and compromising the sensor measurements. For the purpose of demonstration, we assume that there are 2 possible attack scenarios, which correspond to 2 hypotheses. Attack scenario 1: steal water from reservoir 1, turning off the pump P1 and compromise sensor S1 and S2. Attack scenario 2: steal water from reservoir 2, turning off the pump P2 and compromise sensor S1 and S2. The problem is to detect the attack instant and to identify the attack scenarios. In this figure, we compare the performance of the proposed FMA test with the window limited custom, matrix custom, and vector custom test. It can be seen that for given values on the probability of false alarm and false isolation, the probability of misdetection of the FMA test is much smaller than that of the others. In other words, the proposed FMA test offers better statistical performance in comparison to classical algorithm with respect to the transient chain detection and isolation criterion. In this work, we have formulated the attack detection and isolation problem as the problem of jointly detecting and classifying transient changes in stochastic dynamical system driven by unknown system states and random noises. We have proposed also a novel criterion of optimality for the transient chain detection and isolation problem. This criterion involves the minimization of the probability of misdetection subject to given values on the probability of false alarm and false isolation. The attack detection and isolation problem has been solved by revising the analytical redundancy approach, which consists of 2 steps: residual generation by Kalman filter and residual evaluation by FMA test. The simulation results have proven the superiority of the proposed method compared to classical algorithms found in the literature. The limitation of this work is that it is quite theoretical with many assumptions. For example, we have assumed that the attack duration is known, the attack profiles are known, and the attacks are detectable and identifiable. We will try to address such limitations in the future. Thank you for your attention. If you have any questions concerning my work, please send me an email at longdv9@viettel.com.vn. I look forward to discussion with you about this interesting topic. Have good days at the conference. Goodbye.